Hello everyone, my name is Nicolas-Detection from the Department of Civil and Environmental Engineering of the University of Cyprus, and I will present to you my MSc thesis titled Detection and Classification of Construction Objects by Use of Machine Vision and Deep Learning. In this presentation, I will begin with an introduction to the context, followed by research background. In this presentation, I will begin with an introduction to set the context, followed by research background. Then I will detail methodology employed, present results, summarize these thesis findings, and finally I will draw some conclusions and discuss applications for future work. So, the construction industry is an environment that is constantly evolving, presenting both challenges and opportunities for improvement. Some major challenges are related to health, safety, and resource management, requiring technological interventions. Efficient resource management and construction progress monitoring are essential for minimization of delays and conflicts in construction projects. Therefore, artificial intelligence, along with these technologies like machine vision and machine learning, are pivotal in driving advancements within the construction sector. Let's now explore the economical aspect behind the application of AI technologies in the construction sector. In the presented graph in market US, the global generative AI investment construction market for 2023 was estimated at approximately $142 million, and this value is expected to be 20 times higher by 2033. It's also notable in this graph that the significant distribution of this value belongs to machine learning technology, reminding us the importance of this AI technology in the construction sector. So, object detection and classification by the usage of machine vision and deep learning technologies are crucial for performing advancements within the construction safety on aspects of health, safety, and productivity. So this research aims to successfully detect and classify 9 distinct classes of construction site objects, including load-bearing elements, excavators, individuals, personnel, and health safety classes. Additional health safety issues were addressed through the incorporation of warnings for individuals without a proposed safety equipment. Let's now delve into how image classification and object detection tasks function. Image classification involves sorted images into predefined classes based on their visual features, and a successful image classification model can predict the most probable class for new images, providing confidence scores and probability percentages. In contrast, object detection includes identification and localization of specific objects within images or videos by assignment of bounding boxes and confidence scores. Also, this task finds applications in autonomous driving, surveillance, robotics, and many other important sectors. So, this research focuses on automation of detection and classification of construction site objects with a methodology centered around Python programming language. Specifically, Image AI Python library was utilized for the purposes of this research, which is based on Keras and TensorFlow Python libraries. Additionally, custom datasets were created incorporating photos from construction sites, Kaggle datasets, GitHub repositories, and Google image searches. And the Python code was developed integrated with detection models to identify health and safety issues in construction site photos through the assurance of compliance of each human figure with its corresponding safety measures. This table provides a comprehensive overview of the classes employed in this research. As we can see, it includes many load-bearing elements like column, beam, slab. We have some non-load-bearing elements like masonry or windows. And each one of these corresponding numerical code, which was utilized during annotation process, which is a part of the custom object detection methodology. So let's now break down the framework for each task, for each classification. And dataset with over than 6,000 images was created and divided into train and test filters with a split of 80 to 20 train test division. Additionally, the training code by image AI allowed the selection of 4 different algorithms, and a mobile network model was chosen due to its fast prediction speed in comparison with the remaining algorithms. For object detection, a dataset with over than 2,700 images was created and divided into train validation filters. Additionally, 2 algorithms, YOLOv3 and TinyYOLOv3, were both employed for the purposes of this task, along with the variation of other parameters like batch size, number of iterations, and a pre-trained model. In this graph, we have the instance and image distribution across classes for the custom object detection dataset. As we can see, some classes have, like column, beam, and window, have higher number of instances, but also higher ratio of number of instances to the number of images, in contrast with some other classes like excavator, where a much greater quality can be observed. And this phenomenon is to some extent expected for the specific classes. And the accuracy metrics employed for the custom object detection model evaluation. The precision is the ratio of true positives to the sum of true positives and false positives. Recall is the same manipulation of false positives, we have false negatives. F1 score is a more harmonic mean, as it includes the combination of precision and recall in its calculation. And mean average precision of 50%, which evaluates the model's precision and recall at the specific 50% intersection of union threshold, which is the overlap between the actual and the predicted bounding box of a specific object. This flowchart refers to the object detection methodology, which is divided into 2 phases. We have the dataset and training process, where we have the collection of pictures for each custom class. We have the annotation process, the set of training parameters, as I mentioned before, the execution of training code by image AI, and the export of a custom train detection model. In the second phase, we have initially many experiments on both train and random photos. We have the export of coefficient matrix and accuracy metrics. At the later stage, we have the NMS technique implementation in order to enhance model performance and accuracy and export improved coefficient matrix and accuracy metrics. So, as we progress into results section, let's begin with image classification, where a mobile network model was achieved with an accuracy of 81%, with some successful results, but with some fluctuations between the rates of the classes being predicted, mainly due to the fact that the rates are add up to 100%. So in cases with higher number of classes be presented or predicted, we have the higher possibility some of them have low rates. Other challenges we face on this task was some interlighting condition in specific cases or similarities between the classes be presented. Let's see an example. In this case, we have the left figure. It's a random photo for a construction site, and the right figure is the output after the custom model implementation. As we can see, we have 3 classes, main presented and main predicted, but with some fluctuations for reasons explained before, but also for some similarities between some classes like beam column between their visual features. but the overall results seem to be acceptable. For object detection, we have a YOLO v3 model be obtained with an accuracy of 67% on terms of mean average precision, and F1 score slightly above 65%. Validation tests were take place on both trained and random photos with some satisfactory results, but and some phenomena of overlapping bounding boxes. And of course, the fact that the rates are moderate to good give us some insights that this model needs a non-maximum suppression technique to be improved on terms of accuracy and performance. So what the non-maximum suppression technique does, removes overlapping bounding boxes and retains only the ones with the highest confidence scores. Let's see an example. In this case, we have the same photo as I shown before. We have the initial photo in the left figure, and the right figure is the output after the custom object detection model implementation, where we have 8 objects be detected, correctly classified, with very high confidence scores. But some objects in the background are not detected. So why that is happening? Mainly due to the low NMS threshold be applied in this case, which was 5%, and occlusion phenomenon, as some objects in the background, some windows are partially or mostly hidden. And it's also notable that in order to achieve this result, I applied also many rendering settings. This is an example for a health safety application employed in this research. As we can see, we have the left figure that shows us 2 individuals in the construction site. The middle figure is the output after the custom model implementation, where we have correctly classified objects with high confidence scores exceeding 95%. And the right figure is the output after the specific Python code execution, which gave us a warning that we have 2 persons without proposed safety equipment in the construction site. And why that's happening? Because none of the, both of them has both safety helmet and reflective jacket with them in the construction site. This code works with 3 checkpoint stages. The first one checks if we have at least 1 safety helmet and safety vest with the person be presented in a construction site photo. The second checkpoint compare the number of safety measures with the number of persons be presented in this figure, in this construction site photo. And the third checkpoint checks the overlap, the intersection over union threshold between the safety measures objects with their corresponding human figures in order to ensure the compliance of each human figure with its corresponding safety measures. And the confusion matrix, which gave us some insights for strengths and weaknesses for our detection model. And how that works, we have the true positives in the diagonal of this matrix. So in a case of successful detection model, we expect to have an intense diagonal pattern, and in this case, it's not exactly be presented with the initial predictions. From this matrix, an overall F1 score of 61% was obtained, was calculated, and the overall findings underscore the importance of ongoing refinement efforts to enhance models' performance and accuracy. But before we get there, this graph serves as a better visualization tool for the insights of strength and weaknesses I mentioned before, as give us the accuracy metrics for each class individually. As we can see, with initial predictions, we have the majority of classes have moderate to poor accuracy. So, non-maximum suppression technique was needed to be applied in order to enhance model performance and accuracy. And in this stage, we have experimentation with various NMS thresholds be applied. in order to identify the positive and the negative impact of this technique on our model's accuracy. Over these experimentations, we found out that with the decreasing NMS values, we have increased accuracy, but also a significant drop of number of instances. So, additionally, NMS value with 40% threshold was chosen as it serves as an equilibrium between a positive and negative impact. So we have the representing coefficient matrix after NMS implementation. As we can see, we have a more intense diagonal pattern, but also a significant draw of number of instances for each class and total. And the corresponding graph, as we can see now, the majority of classes have high accuracies, exceeding 70 or 80%, and an overall F1 score accuracy slightly below 80%. So, summarize these thesis findings, we can say that we have an image classification model obtained with 81% accuracy, but with some fluctuations due to the fact that the rates are not 100%. An object detection model with 67%, but which was struggled with overlapping bounding boxes for specific objects. And non-maximum substitution technique was needed to improve this model performance and accuracy. And some conclusions for the end. This research work can be expanded, firstly, by the expansion of the custom datasets deployed, by maintaining quantity, quality, and balance. Additionally, future research could also categorize object classes into purpose-specific groups for better applicability in construction site management, like machinery, materials, vehicles, individuals. Also, improvement annotation of actions and in conjunction with NMS technique are needed in order to enhance the detection model performance and accuracy, but also to perform sharper results. And finally, image AI can be explored for other custom activities that provide, like video streams. Thank you very much for your attention.